Hello, everybody, and welcome to your channel, Thermal Engineering Concept and Principle. This is a special issue to cover our efforts that have been presented during the last year, corresponding to the second anniversary of your channel. I hope that I can introduce summary for the published episodes as short videos or long videos in this channel in the field of energy, heat transfer, energy management, and uh, renewable energy sources. Let us go to what have been done during the first and second year of the life of the present channel. Thank you for your continuous support, and I hope that I will continue to present videos in different sectors of industry in the field of thermal engineering to achieve our goals, that is, a free education for all.
Welcome to my channel Thermal Engineering. I am Ali Tarrad, and after 35 years of experience in engineering, I still think it is fascinating. This is my first attempt on this channel to give back to the scientific community. So I appreciate your comments, feedback, and what subjects that you would like me to cover in the future. Let us start with heat transfer modes. Here we have some of the contents which has been published uh, in this channel. We passed through heat transfer modes, their applications, industrial applications in heat exchangers, water chillers, cooling towers, and many other industrial and technological parts in this field of engineering, where energy is the principal uh, factor in these equipment. We also passed through thermodynamics of Rankine cycle. The main components of this cycle, which is used in uh, electricity production in power plants. We applied first law of thermodynamics and waste energy recovery. How can we use it to produce electricity and improve the efficiency of plants? We also focused on the geothermal energy in power plants and heat pumps. And finally, we arrive to the thermal design of geothermal borehole.
During the second year of the life of this channel, we focused mainly on geothermal energy, where can be used as a part of heat pumps for heating and cooling systems, and how can we achieve the thermal design of such heat exchangers, which are called ground source heat exchangers. Then we have some issues and topics related to heat transfer, mainly convection and condensation, for both single and tube bank, internal or external flow. We have introduced also some of the air conditioning and refrigeration terminology and applications. And for the heat pumps, we have something related to the uh, types of these heat pumps, and uh, depending that on the source or the available source of energy, such as air or a geothermal heat pump. And finally, we have presented two webinars in the field of hydrogen and geothermal energy, and the other one was about an overview of renewable energy sources, and where we can use earth as energy source for heating and cooling systems.
Borehole depth estimation. In this episode, I will introduce another relation which has been derived and published by me to find out the depth of the geothermal heat exchanger. Let us consider a U-tube with specified dimensions denote S sub P, which represents the distance between the centers of the two legs of the U-tube, and borehole diameter. Let us find an equivalent diameter from the assumption which has been based on the idea of keeping the volume of the filling or the grout is constant in both geometries, the equivalent and the original configurations. So this assumption will produce the equivalent diameter of the tube to be square root of 2 times d naught, as represented in equation number 1. And this equation has been derived by many investigators in the open literatures, and can be found even in the present reference of the present correlation. And let us transform the equivalent tube to the form which is shown on the right hand side of the above illustration, and to keep the shank distance between the original and the equivalent geometries constant. That is d sub s equal s sub p minus d naught, which is equal to s sub p e. E here refers to the equivalent minus the equivalent. And with some analysis and interpretations which have been described in the original paper, we have arrived to L sub PE nearly equal to L sub P plus 0.207 times D naught as represented in equation number 3. And L sub PE represents the distance between the center of the equivalent diameter and the center of the borehole. And in that case, we will get an offset or eccentric cylinder in the outer one. Then we may calculate R sub F in the form of equation 4, which has been already mentioned in the previous episodes and can be found in textbooks such as Holman, that is heat transfer, and even in the reference of the present model, you may find this equation as well. And the reference is presented in the list of the references, which is situated at the description box below the video of this episode. To analyze the borehole with a double U-tubes, let us consider that we have this arrangement of a double U-tube heat exchanger with design specifications S sub P, D naught, and D sub B for the borehole, and it is surrounded by the soil. So how can we deal with the double U-tube and to model it and analyze it to get a final form of equation where we can use to predict its depth? Let us go back to the same assumptions which we have used previously, where we can consider the grout material volume is the same for both the original design and the equivalent design. And let us assume that we have W tube, they are identical and similar in their dimensions, such as the length and the diameter. So we can consider the inlet part, which is shown in the green color, or even the exit part, which is shown in the blue part. If we consider the inlet part, then the volume of the grout should be constant and fixed for both geometries, which leads to d equivalent equal to square root of 2 times d naught, which is the same form which we have obtained throughout our discussions for the design of a single U-tube. Now, let us transform this geometry to equivalent one as shown in this figure. Then we have the inlet part, which is represented by the green, and the exit part, which is represented by the blue. And generally, for the previous episodes where we have used uh, the similarity and analogy between the thermal resistances and the electrical circuit resistances as shown in this figure, and we have derived the borehole um, thermal resistance, and you may find a full description of the present analysis in this reference where could be found in the list at the bottom of this video in the description box, which is represented as the first reference in the list. And we have here five thermal resistances. For two of them are for the pipe, which are identical and similar and equal. And then we have the thermal resistance between the surface of the tube and the grout material. We have two legs here, then we have two resistances, and one is the resistance of the shock between the tubes. Turbulent flow correlations. There are quite good number of correlations that are published and can be found in the open literature. One of the oldest correlations is called Cedar-Tart correlation, which was built in 1936, and it depends on the Reynolds and the Prandtl numbers for limitations and conditions as shown in equation number 1. Then we have Pitopov in 1970. Again, this is presented in a form that Nusselt is a function of Reynolds and Prandtl with the effect of viscosity and the length of heat the pipe, and we should mention that the properties or thermal properties of fluid usually are based on T bulk or TF. T bulk, T sub B, and T sub F represents the film temperature. Then we have Genitsky, that is presented in equation 3a and 3b, depending on the range of Reynolds number. And finally, we have a Tarrad correlation in a simple form, in fact. Its Nusselt number is a function of Reynolds and Prandtl. For water, of course, this correlation, and it has been produced from a bank of data obtained from practical field in surface condenser that is used in power plants. And we have the temperature T sub B equal to inlet and outlet temperature divided by 2. And film temperature represents the T bulk plus T sub wall divided by 2. And all these correlations have limited range for Reynolds and Prandtl number in their application. There are quite a good number of these correlations which can be used to predict the condensation heat transfer coefficient over tube bank. In this table, I will mention some of them. Maybe Jacob in 1949 based his correlation on the single tube condensation on horizontal tube presented by Nusselt in 1916,
by adding the effect of the condensation which passes from one row to another, uh, and that will reduce the overall heat transfer coefficient, of course, because the condensate will cover more surface area, and then it will add um, a resistance to the condensation process at the surface of the rose after the second. And then when you go to the third, it will be more difficult as well, and the heat transfer coefficient will be less, and so on. So he has added uh, um, a sort of correction to the single tube condensation by using equation 1b, where n sub r represents the number of tube in a vertical column to the power minus quarter. And then Kern presented the equation which is based again on Nusselt equation by using nr to power minus 1 over 6. And he said that the presentation of Jacob with equation 1b, it is really a conservative and will predict low heat transfer coefficient, which requires or overestimate the surface area of the condenser. Planck in 1978 suggested multiplying the single tube coefficient as presented in equation 1a by Nusselt by a factor of 0.7, and using nr to power minus quarter is similar to that of Jacob. And this suggestion was based on experience and uh, practical experimental data available for condensation process. And finally, Tarrad in 1997, again, he has based his equation on Nusselt equation 1a, and nr is raised to the power minus 1 over 5. And this suggestion was based on the assumption or fitting of the available experimental data as collected from steam condensers in power plant. And it gave about 95% of the data lied on this line of correlation. These equations, and you may find more of these correlations. I will put some references in the a link uh, seated in the description box below this video. In an air-to-air heat pump operating in heating mode, thermal energy is transferred from outdoor air to indoor air using a vapor compression refrigeration cycle. First process occurs in the evaporator. The outdoor unit absorbs low-grade heat from ambient air as the refrigerant evaporates flow pressure and temperature. Second process occurs at the compressor. The compressor raises the refrigerant pressure and temperature significantly, approximately in isentropic compression. The third process occurs in the condenser. The indoor unit releases this heat to indoor as the refrigerant condenses at high pressure. The fourth process occurs through the expansion valve, where it reduces the refrigerant pressure, completing the cycle. Electrical work supplied to the compressor enables heat extraction from outdoor air and delivery to the indoor space, typically achieving a coefficient of performance greater than 1. Here we have the direct contact geothermal heat pump, where earth is considered as a heat source. In heating mode, a geothermal heat pump with a direct contact, which is known as TX or direct expansion, ground heat exchanger operates as the following parts. First, heat absorption in a ground loop, which is considered as evaporator in ground. Liquid refrigerant, for example, R410A, is throttled to low pressure and circulated directly through buried copper tubing. Because its saturation temperature is below the ground temperature, typically between 10 to 18 degrees Celsius. It evaporates by absorbing sensible heat from the surrounding soil. And then this vapor passes through a compression process where it is compressed to a high pressure and temperature. Once it has compressed to these conditions, it passes through a third stage, which is called heat delivery indoors. Usually it is condenser in building. The hot high pressure vapor flows to the indoor heat exchanger, where it condenses and releases latent heat to the building air or a hydronic heating system. Finally, the liquid, as it leaves the condenser, passes through expansion and recirculation uh, process. The condensed liquid refrigerant passes through an expansion device, reducing its pressure and temperature before returning to the ground loop to repeat the cycle by following the blue side of piping. In this webinar, uh, renewable energy overview has been presented where we can use hydrogen and geothermal energy in a clean environment, and the types of hydrogen and um, geothermal heat pumps and how can they be used um, are presented in this webinar in April 2025.
أعزائي وأصدقائي المتابعين وزملائي، نقدم في هذه الحلقة موضوع قد تم تقديمه سابقا ضمن ندوة أقيمت بالتعاون مع كلية البوليتكنيك للتخصصات الهندسية في الجامعة التقنية الوسطى في العراق، حول استخدامات طاقة باطن الأرض في التدفئة والتبريد تحت عنوان نظرة عامة على مصادر الطاقة المتجددة، توظيف باطن الأرض لأغراض التدفئة والتبريد. وضمن هذا الجزء الأول سأقدم بعض التطبيقات ومدخل لمفهوم استخدام طاقة باطن الأرض أيضا لأغراض التدفئة والتبريد. ثم في الجزء الثاني سندخل في مجال الحسابات والتصاميم الحرارية لهذا الاستخدام. أشكركم جدا على المتابعة، ودعونا نذهب إلى مفردات ومحتويات الجزء الأول من هذه المحاضرة.
أصدقائي وزملائي الأعزاء، نستكمل الجزء الثاني من الندوة التي أقيمت بالتعاون مع جامعة التقنية الوسطى، كلية البوليتكنيك التخصصات الهندسية، في ورشة عمل كانت مخصصة للتعرف على مصادر الطاقة المتجددة، وكان موضوعها نظرة عامة على مصادر الطاقة المتجددة، توظيف باطن الأرض لأغراض التدفئة والتبريد. وفي هذه الحلقة سنغطي الجزء الثاني والأخير من هذه الندوة، آمل أن تستفيدوا زملائي وأصدقائي من هذه المحاضرة وما تحتويه من معلومات مهمة حول مبدأ Geothermal Energy وتطبيقه لأغراض التدفئة والتبريد. وهناك الكثير حقيقة من المحاضرات التي أعددتها سابقا موجودة على شكل حلقات فيديوية في قناتي اليوتيوب. كما تعرفون هي تحت اسم الهندسة الحرارية، المفهوم والمبدأ، وتسمى أيضا Thermal Engineering Concept and Principle. دعونا نذهب إلى تفاصيل محتويات هذا الجزء.